My name is Darell Kotton. I'm the director for the Center for Regenerative Medicine of Boston University and Boston Medical Center. And we're sitting here in our conference room in the middle of this center, which we affectionately call the CREM, C-R-E-M. I'm called a physician scientist, so 20% of my time is clinical, seeing patients, usually in a teaching role with let's say a pulmonary or critical care fellow, a specialist doctor. So we have a lung clinic, or I'm in the hospital on consultation seeing lung patients or in the intensive care unit. And 80% of my time is spent in research, in part as a principal investigator running our laboratory, performing lung research on stem cells. And part of my time is directing our center, which is a multidisciplinary effort and around us on this floor of multiple labs working towards the same mission of engineering regeneration. So I was born in Johannesburg, South Africa, and my family immigrated when I was 10 years old to Cleveland, Ohio. So I went to high school, college, and medical school in the USA. And my father was a physician, and I wanted to be a doctor. I was interested in science and medicine, and so I was pre-med in college, and I was also interested in music, so I took some time off, a year off before medical school, to go to Berklee College of Music and study guitar. So I think I'm just generally interested or curious in things. But I was pretty certain I wanted to be a doctor, and I went through medical school and enjoyed it and was excited to train as a pulmonary and critical care specialty physician. And during my fellowship, it was only then that I did a lab rotation with a mentor who I liked very much, who really stimulated me to consider other things I'd never considered before, and I quite unexpectedly found a love and passion for basic science research in the laboratory, and so I really changed my career after I had completed medical school. So the focus of my lab is lung regeneration and lung stem cells, and so we have many projects that are usually led by each student or trainee or junior faculty member in the lab. The easiest way I can explain what we do is that we think about people walking around with diseased lungs, like somebody with emphysema or cystic fibrosis, for which there are limited treatments, and we think about what would it take to make new lung cells for them, and if they were their own lung cells, in a laboratory, could those lung cells predict which drugs might work for that individual? And one day, could we use their own lung cells that we might engineer for them? Could we use those to build functional lung tissues or entire functioning lungs that we could put back into the patient and one day have a cure, a new lung that was theirs, or a new lung cell that would engraft into them to help heal their diseased lungs. So we can't actually get stem cells from people. We don't know how to get them. We don't know where they are, the right stem cells. So we have to make the stem cells ourselves from the person. So we take a blood draw, like you give blood when you go to the doctor, except we take their living blood cells back to the laboratory, and we use this technique to change their blood cells all the way back into a stem cell that looked essentially like when they were a fertilized egg. And since the cell looks like when they were an embryo, we can coax that cell forward to become anything in theory, but our goal is to coax it forward into a new lung cell. And you can imagine that takes a lot of work and is very tricky. It's not a one-step recipe to take a cell that looks like when you were 3.5 days after fertilization, a little embryonic cell, and push that all the way forward through what you did in 9 months of development as a fetus to come out with a real functional, good lung cell. That's the main hurdle that's facing us that we hope to solve through our lifetime of work. My dream would be that in the end our work would have resulted in the ability to take stem cells that we can make from any patient with any lung disease, really, but especially those diseases that have no cure or treatment currently. And my hope would be that the patients one day with those diseases could have a stem cell made from their blood, coaxed forward into real lung cells, and those lung cells could have the gene defect responsible for their disease fixed, and those cells could be put back into them. I don't know the form that they'll be put back into, whether it's a whole bioartificial lung or one cell at a time or one tissue at a time, but my hope is those patients will be breathing easier, be cured, and that when a parent here's their child's diagnosed with a devastating disease or a genetic lung disease of any kind, really, that parent will be given a plan that many scientists spent their lives working to achieve that plan, so their child will have hope, won't have to suffer, and can grow up a normal child in the playground. That's the hope. We're really aware that we're committing to something much greater than ourselves here, and that the end goal may only be reached by our trainees or those who come after us, and we may not live to see that day, but that really doesn't in any way detract from the work or the marathon we run. It's really a great journey.